Defining what the column space is. Remember, the column space of an n by n matrix is all the linear combinations of the columns. And we also thought about the column space as kind of the range or the outputs of the matrix. If you think about the matrix as a function. So now we just want to work with some basic exercises. Do some basic exercises. So here our first exercise is to find M such that the column space of A is a subspace of Rm. So basically here we're just going to look at how many rows we have, right? This is a, 4 by 2 matrix. So we're going to say here that the column space is a subspace of R4. You focus on your number of rows, actually. Is a subspace of R4. Yep, because the column space is a linear combination of those two columns. So if I make up linear combinations of those two columns, they're going to have 4 entries, right? 4 entries. Those vectors. All right, so number 2. So you got another matrix, capital A. It looks like 1, 5 in the first column, second column is 2, 6, third column is 3, 7, and the fourth column is 4, 8. So if you look at this matrix, it has basically 2 rows, right? It's a 2 by 4 matrix. So the subspace will be, column space is going to be a subspace of R2. Column space of A. Yeah, so imagine you're taking those 1, 2, 3, 4 columns, and you're making linear combinations of those columns, right? You're only going to have 2 entries. For any linear combination you come up with, you're going to only have 2 entries. So we're in R2. The linear combinations are. All right, where else? Another type of exercise. Exercises. Determine if the vector B is an element of the column space of the matrix A. So I'm going to give you a vector, B, in a matrix A, and we're going to see, okay, is B in the column space of A? So B is going to be 5, -1, 6, 9. And B is going to be the matrix consisting of columns 5, 1, 2, 3, and let's see, 0, -1, 2, 3. Okay? So basically what we have to figure out is B a linear combination of the columns of A. So we're going to have to essentially consider, so in other words, we're going to ask the question, well, let me use a different color. Let me use red. Is AX equals B consistent? Does it have a solution? So the matrix vector equation AX equals B, does it have a solution? If it has a solution, then yes, B is a linear combination of columns of A. So we're going to set up an augmented matrix to test whether there's a solution or not. Augmented matrix. So we're going to put down the matrix A here, and the vector B augmented on the side. So we're going to have what? 5, 1, 2, 3. And what? 0, -1, 2, 3. And then on the right-hand side, 5, -1, 6, 9. And we're going to row reduce that, RREF. And I row reduce this in advance. I'm going to get 1, 0, 0, 0 from my first column. My second column, I'm going to get 0, 1, 0, 0. For my last column, I'm going to get 1, 2, 0, 0. If you look at this carefully, this is actually a consistent system, right? You don't have zeros and then another number. You don't have zeros and then another number, so you don't have any inconsistency. So actually we're going to have, this is consistent, right? Basically x1 would be 1 and x2 would be 2. So your vector x, your solution vector x would be 1, 2 right here. So it is consistent, right? Ax equals b is consistent. You don't actually have to write the solution, but I'm going to go ahead and write it with solution 1, 2. So since there is a solution, then B is in the column space of A. Therefore, B is in the column space of A. So maybe some of you had some problems if you were using a TI-83 or TI-84 calculator. Sometimes you might get a dimension error problem when you're trying to row reduce that. That's because you have more rows than columns. So if I were putting this in a TI-84, you want to set it up as a you want to do a 4 by 4 matrix. So basically, the way you would put it in a TI-84, TI-83, I believe you have to put in like this. You have to put in 1, 0, 0. Oops, what am I doing? Let's put it in 5, 1, 2, 3, 0, negative 1, 2, 3, 5, negative 1, 6, 9. And then you have to add a column of zeros like that. So when you row reduce it, then you can row reduce it with RREF. When you row reduce it in the TI-83 or TI-84, you should get, it should work out. Yeah, you get like 1 and a bunch of zeros. 0, 1, 0, 0. And then you're going to get 1, 2, a bunch of zeros, and you get a bunch of zeros here. You just kind of disregard that right-hand column. They just kind of disregard that column and imagine there's a bar right there. So that's what you have to do when you're doing the TI-83, TI-84. Yeah. Because you get a dimension error when you put more columns than rows. Yeah. So you have to make sure it's 4 by 4. All right. What were we doing? I forgot. Exercises. 2. To determine if B is in the column space of A, here's a vector B, right? 9, 10, oops, equals. So that's my vector, and my matrix A consists of 1, 2, 2, 4, 3, 6, 4, 8. And I want to see, okay, is B a linear combination of the columns of A? So that's the question. Is AX equals B, that linear system, consistent? Is there a solution? So to figure that out, we'll set up an augmented version of this system, an augmented matrix that represents this linear system. We're going to have what? 1, 2, 2, 4, 3, 6, 4, 8. And augment that with 9, 10. You shouldn't have any problems entering that in your calculator. You RREF that dude. And when you RREF that dude, I'm getting 1, 2, 3, 4, 0, and then 0, 0, 0, 0, and 1. So immediately you see that this system is inconsistent here, right? If you were to convert that bottom line there, into an actual equation, that would be 0 equals 1, which is not true. Never is equal. So since the system is inconsistent, since x equals b is inconsistent, that means you can never plug in anything for x to get out b, since x equals b is inconsistent. Then b is not an element of the column space of A. So B is not a linear combination of columns of A. Yeah. Okay, we want to do one more exercise here. This is something we've actually done in a previous video, but now we're just going to talk about it in terms of the column space. Show that H, which is a set of vectors, taking on the form 5 x2 minus 3 x3 x2 x3 9x2, this set of vectors in R4, such that x2 and x3, these two parameters, are real numbers. Show that this set of vectors in R4 is a subspace of R4. Without using the subspace test. This is not writing without using the subspace test. So remember the subspace test, you have to show the 0 vectors in there, you have to show a sum of 2 arbitrary vectors from the set is in there, and to show that scalar multiples are in there. So I'm not gonna use that. I'm not gonna use that. So we're gonna just gonna okay. So let's note that H is what 5x minus 5x2 minus 3x3 is a typical first entry. X2 is a typical second entry, x3 is a typical third entry, and a typical fourth entry is 9x2. That's what your vectors will look like in H. So H is a set of vectors taking on this form. X2 and x3 are real values. Let's scroll. Let's write this in parametric form. So this is equal to the set of, so I'm going to factor out an x2, and I'm going to have coefficients 5, 1, 0, 9 for x2. Then I'll factor out an x3. I'll have coefficients, what, negative 3, 0, 1, and 0. And x2 and x3 are arbitrary constants. Call these parameters. They can take on any value they want. But what is this equal to? This is just the span of those two vectors. Those two vectors, the vectors being 5, 1, 0, 9, and negative 3, 0, 1, 0. And what's that? That's just the column space, right, of the matrix. That's just the column space of the matrix consisting of entries 5, 1, 0, 9 going down the first column, negative 3, 0, 1, 0. So in the column space of any matrix is a subspace of R, in this case 4, right, because we have 4 entries. 4 entries, which is a subspace of R4. Yeah, we proved that, right? Column space and the span. Column space and the span are the same thing. That's it. That's the end of the proof, right? The column space is a subspace of R4, but that's just H. So we've proven that H is a subspace of R4. That's what we wanted to do. Nice.